because also the last paper cannot be here, but they prepared the presentation clips for us. Their title is Novel Topic Distribution Prediction Using Latent, Semantic, and User Behavior. And after the video clip, we can ask the author online. You can connect by Skype to ask the question.
Hello, I'm Zhou Hu. I would like to present our study on novel topic prediction using Latent, Semantic, and User Behavior. There are three authors of this paper, since Semantic is their potential leading, and we are from Diffusion and learning on network person. So let me start from introducing the diffusion prediction. So there are a lot of diffusion and big social networks such as learning. So here we can find diffusions as a post-response behavior on certain topics. For example, suppose U1 user U1 posts an article related to topic HTC and the user replies to U1. So we suppose that in this scenario, U1 actually diffuses an information related to the topic HTC community. And suppose the user also responds to this article. And as we assume that U1 also diffuses HTC community. So this type of prediction of this diffusion is usually happening in research topic. However, most of the studies focus on prediction of existing topics. For example, suppose one produces HPC community user, and then there is a new user who will diffuse HPC community. So this is what I think will start. But in our problem, we want the diffusions of novel topics. So, for example, can we predict diffusions of a topic F7 using diffusion of existing topics, with no attributes, as well as keywords of existing and novel topics? So, actually, this is not an easy problem because we did not have any previous record about iPhone 7, the diffusion of iPhone 7. And to make this problem harder, some users may start diffusion even if they never is. For example, the user never have any diffusion before. So can we predict the iPhone 7 diffusion between them? Or another case is the user U5. So there is never this user never diffused any information before. So in this case, can we still predict the diffusion related to this user? So we argue that this kind of diffusion prediction for novel topics actually have valuable applications. For example, in advertisement, Apple might want to decide the test users of iPhone 7 to maximize the propagation effect of this product. And some politics parties might want to estimate the response of, say, tax policies before they bring it to public discussion. So to solve this non-trivial problem, we propose some intuitions. So the first one is that we can explore the hidden semantic information of the topics. For example, even if we don't know, even we don't have any previous diffusion record of iPhone 7, but since we have previous diffusion records of other topics, and then suppose we know that iPhone 7 is more similar to HTC or iPad, but not as similar to Taipei 101 or Facebook. then we can estimate that the diffusion from U3 to U4 related to iPhone 7 might be has higher probability than others, because U3 and U4 talks about HTC and iPad before. So for us, we can understand, for us human, we can understand that iPhone 7 is related more to HTC and iPad than to 101 or Facebook. But how can the computer know the relationship between the topics? So here we apply topic model. So in our experiment, we use Latent direction allocation, or LDA, to let the computer understand the relationship of the topics. So here, LDA can be considered as a metric decomposition. So we basically decompose topic to words matrix to the multiplication of two matrices, which are topic to hidden topic category matrix and hidden topic category to words matrix. So we use LDA to do this decomposition, and then we extract each row of the topic to hidden category matrix as a feature. So here we can build the topic relationship based on the similarity of these rows. So for example, suppose we want to know the similarity between iPhone 7 and HTC, then we can compute the cosine similarity of the red row and the blue row. And then we can also compute the similarity of iPhone 7 and 101 based on this cosine similarity of the red row and the green row. So in this way, a computer can understand the connection of the topics. For example, iPhone 7 is actually more similar to HTC than iPad 101. So this is the way we can use the topic information to do prediction of iPhone 7, even if we don't have any previous record about iPhone 7. And the second intuition is that we can apply user information. So we extract hidden behavior of the users, for example, modeling the characteristic of the users by using their input output words. So in here, U4, in our example, U4 might be a good listener because this user receives various kind of information. So we might have an estimation that U1, U3, or U1, U2, or U3 to U4 might have higher probability. So we can use the LDA to model user information based on the contents positive or replied by the users. And the third intuition is the user topic information. So we can model how users like hidden semantic information of topics. So in our example, users might tend to talk about information in certain domain. For example, U1 always talk about HTC, while U2 and U3 talk about diverse topics. So suppose iPhone 7, we know that it is more related to HTC, then the user U1 who likes HTC likes to talk about HTC, but might also like to talk about iPhone 7. So the diffusions from U1 to U2 to U3 and to U4 might have higher probabilities than other users. So we again can utilize the LDA results from topic information to estimate how the user would like the new topic or concept. And then the next intuition is to use the global information. So for example, good friends may talk about more diverse existing topics. So in our example, U2 and U4 talks about 3 different topics. So we assume that they might also interested in producing new topics. So here we can predict based on such kind of information by checking the divisions of existing topics. And the next intuition is about user behavior. So the idea is that first of the filter flock together. So in our example, so suppose user U1, U3, U5 are males, and U2 and U4 are females. So if we can identify that male user actually tends to diffuse technology topics than females. And then iPhone 7 is actually more like technical topics like HPC or iPad. So then we can understand that U3, the link to diffusion from U3 to U5 about iPhone 7 might have higher probability than from U4 to U5. So in this way, we can actually predict unobserved predictions because unobserved diffusions. Because even if we don't have any previous diffusion record for example, the user U5 here, but we can use the users with the similarity attribute with U5 to estimate the possible diffusions of U5 for this novel procedure. So here, the attribute might be like gender or language or any other kind of features. So the next and the final intuition is that we have such kind of different type of information and each with a score assigned to the diffusions. So how can we combine them, but without knowing the usefulness of them in advance? Because it is very hard for us to determine which information is more important than others in advance. So the idea is that we can train a classifier to get probability. So we basically extract features using information of, and then we learn the importance of each information using the classifier, and then finally we use a trained model to predict the diffusions. So the idea of our methodology is that we use latent, semantic, and user behavior in a supervised learning framework based on the previous 6 intuitions. So there are 3 inputs of our method. The first one is a social network with no attributes, and then the second one is diffusions of existing topics, and the third one is a set of keywords for each topic. And then we extract features based on the first 5 intuitions, and then generate the features and then feed them into a binary classification. In our experiment, we use linear SVM, and then we can get the predicted diffusions of the novel topics. So here are our experiment results based on the plug dataset with about 700K diffusions within 100 topics. So here we have 7 baseline single features, and then we illustrate 8 user behavior single features, and then we also try to do feature selection to identify the best combination of features. So as you can see, user behavior single features, the best user behavior single feature actually outperform the best baseline single feature for 3% in terms of AUC. And for the best combination, the improvement can boost to 6%. So based on our experiment, we identified that in this scenario, simple baselines actually perform better. And if we use the user behavior features, then they are actually useful and can beat all baselines. And then if we combine the user behavior feature to latent semantic feature, we can provide further improvement. So the contributions of our study is threefold. First, we propose a challenging test to predict unobserved diffusions. And next, we utilize latent, semantic, and user behavior to solve this challenging problem. And third, we provide promising results to show the usefulness of our model. So we also release our data set on this link, so if you are interested, you can visit our website and download this data set. So thank you very much for listening presentation. And if you have any further questions or suggestions, please feel free to contact all of us. Thank you very much.
Hello. Can you hear me? Hello. 中听过 Can you hear me? Hello? Can you hear me? Okay, but I cannot hear you. I just watch you. So, can you speak loudly? Maybe just.
Hello, can you hear me?
Oh yes, yes. And can you hear me?
Yes.
Okay, thank you. Thank you.
Thank you.
Your presentation clips. And in Zhongguo, right?
Okay. Yes.
Okay. I ask the question for you. Yeah.
Okay.
Yeah. I because you talking about the semantic. Yeah. But I don't know how to segment the keyword from you use the prompt data set, right? Yeah, so I don't know how to segment keyword to combine. For example, if you recognize HTC and HTC M5, and you know my question? Because they are different concepts.
Right.
But maybe you don't consider this issue in your presentation. Okay.
Yes. Actually, we collect our data set from selecting keywords first. So we collect the top 100 hot topic from Blur, and then we try to collect the messages related to these 100 topics.
Yeah, so you trust the prompt result.
Yes.
Okay, sure. Yeah, but for example, if the company, HTC company, hold a new mobile device event in 101, do you know my question? And you can get some message talking about the HTC company take some event in 101.
Right.
Yeah. So when you calculate the topic model, the HTC and the 101 will be very related.
Yeah, that's right. So this is actually one of the limitations of our work, because we use LDA topic model, which is based on the co-occurrence of the keywords. So it is pretty hard to distinguish this situation based on our current framework.
So, any solution?
Maybe in the future we can consider to collect more context of each concept. For example, we can crawl the web and understand that HTC is actually a mobile phone company, and 101 is actually a building or a venue, so that we can distinguish their difference. For example, one possible way is to use word embedding. So in this way, maybe we can overcome this problem.
Yeah, okay, thank you. I have another question.
Okay.
In your experiment, how to evaluate the unobserved prediction or unobserved diffusion? You are talking about yeah.
Right. So
how to evaluate it?
Yeah. So our way to do this is that because we do cross validation based on each topics. For example, in one fold we use 75 topics for training and use the rest 25 topics for test. So to define the unobserved one, we define unobserved diffusions as those appears in the test diffusions, but not in the trained diffusions. So in this way, we can try to identify those unobserved ones.
Okay, so you just to treat testing diffusion as the unobserved diffusion.
Yeah, if it is not, if the diffusions was not observed in training set. For example, suppose there are two people, A and B, and they have some interaction, such as cause and response in training. Then we will consider this as this is an observed one. But if they only talk in test set but not in train set, then we consider this as an unobserved one.
Okay, thank you. So
thank you.
Any other question? Because we have more time to end this session, so we can ask more questions. Any other question? No? No question? Okay, and I think we have no further question for you. Yeah.
Okay.
Yeah. Okay. Thank you.
Thank you very much.
Okay. Yeah. Okay. We the white paper all presented, and I want to close this section. Thank you for your attention and joining this session here.